Hello, my name is Martin Sueldia, and I'm a postdoc at the TU in Dublin and the University of Amsterdam. And today I'm going to talk about the paper titled Minimizing Delay in Distributed Service Systems with Redundancy and Random Slowdowns. So this is the outline of my talk. First, I'm going to introduce the general partial forejoin model with redundancy. And then throughout the talk, I'm going to introduce two slight variations of these models with different assumptions for the slowdowns. And for each one of those, I'm going to give a delay lower bound, and I'm going to introduce asymptotically delay optimal policies. So let's jump into the general forejoin model. So this is a model where distributed service system, where on the one hand, we have n servers, homogeneous servers, where each server has a first in, first out queue with infinite capacity. On the other hand, jobs arrive as a renewal process of rate lambda n over kn, where lambda is a positive real number and kn is a positive integer. The actual jobs have size that are RID with mean kn. And actually, jobs consist of kn tasks of equal size that can be processed separately. And a job is considered done when all of its tasks are finished processing. Now, in the middle, in principle, we have a controller that gets to decide where to send these tasks. Now, we have two extra features for this model. One is the ability to create redundant tasks or replicas. By this, I mean that the kn tasks of each job can be encoded into any number of at least kn replicas, such that the job is still done when any kn of the replicas finished. So you can think about maximum distance coding and trying to retrieve a file from coded pieces of the file. Then any kn of them will do the job. And we also assume that when any kn finish, then the rest are canceled immediately and leave the system along with all other tasks of the same job, all other replicas. And the other feature is service slowdowns. And the key principle behind this is that the service processing rates, actually, they're not constant, but fluctuate over time. For example, due to thermal throttling or other background processes in a server. And in order to model this, we assume that the server's time of the ith replica of the j's job can be expressed as the product of the size of the replica times 1 plus a slowdown. Now, right now, we're not going to introduce any more assumptions on the slowdowns. That's going to come later. So what's the problem? Well, first, our objective is to find policies that minimize the delay of a job as the size of the system goes to infinity. To be more precise, the delay of the job is the time between the arrival of the job and the time when any kn of its replicas finished their service. So this means that the delay of a job is the knth order statistic of the delay of its replicas. So if you think myopically, actually, okay, it seems that the more replicas you create, they're probably going to be on shorter queues. So we're going to observe less queue and delay for any given job. And even if there's no queuing and all replicas start a service at the same time, because of the slowdowns of the servers, then if we create more replicas, we kind of obtain the benefit of the faster servers, and we see smaller service time. But there's a problem with the myopic intuition is that more replicas could possibly create higher loads, thus increasing the queuing delay or even completely destabilizing the system. So what are the practical issues, practical questions that we need to solve? First, how many replicas are too many for this destabilizing the system? If we should adapt replication to the level of congestion, if it's less congested, probably maybe more replicas can be created. It should be create more replicas if a job is taking too long to finish. And last but not least, whether bigger jobs should be replicated more or less than smaller ones. And today we're going to answer all these questions for two different models for the slowdowns. The first model is the independence exponential slowdowns. And now the motivation behind this is that we observe that the long load times from the Amazon Web Servers are shifted exponential random variables. So if we recall that the service time of the ith replica of a job is the size of the task times 1 plus slowdown, then in order to this coincide with the data, we assume that all the slowdowns are IID and they're actually exponential with some mean 1 over mu. And this is actually a special case of the S and X model introduced by Christian Gardner and others in 2016 for the case that they're actually exponential random variables. So we first start with the universal delay lower bound. So we had a controller there. We're assuming that the controller knows the full queue state, including elapsed times, but not include remaining service time, but because that would kind of trivialize the problem. We assume that the controller can create the replicas at any time, so not only at the beginning when the job arrives, but any time after that, it can also create replicas for jobs. Also, we assume that this is a little restriction that the controller cannot prematurely cancel replicas in service. So it can cancel any replica that it's waiting in a queue, but once a replica starts its service, it's got to be in service until all any KN's replicas finish service of that job. Then kind of a first result is that there exists a stable policy if and only if this R star equal to 1 over lambda minus 1 over mu, so the expected interval of times minus the expected slowdown is bigger than 1. And then for any stable policy, we know that the expected delay is lower bounded by this quantity. That doesn't depend on n, only depends on kn, mu, and r star, so it also depends on lambda. An interesting thing about this formula, it's kind of complicated, but actually if r star times kn is an integer, then this lower bound is the expectation of the kth order statistic of r star kn service time of replicas. And we can actually use this to kind of try to construct an asymptotically optimal policy. So one straightforward thing to do would be okay, if r star times kn is an integer, then we create this number of replicas per job and we send it to idle servers. So yeah, that's easy, right? Well, not so fast. Actually, first trivial problem, r star times kn might not be an integer. And also creating this number of replicas per job actually destabilizes the system with load equal to 1. So barely, but it's still unstable. So the solution is actually first, we can create, regardless of r star kn being an integer or not, we can create a mixture of the ceiling and the ceiling minus 1 of the number of replicas. And we actually create a mixture such that in average, we have slightly less than r star kn replicas per job. So the system is always stable and we force a heavy traffic. So in the limit, we're utilizing all the resources. And we just need to have a policy like join the LQ such that if possible, they send all replicas to idle servers. As for the delay performance of these policies, first for a case of kn equal to some k independently of n. First we plot the lower bound, so we have the lower bound as a function of r star of lambda, so that is we keep mu fixed and we move lambda from the maximum value. When lambda is the maximum value, r star is equal to 1, and then when lambda goes to 0, it goes to infinity. So with the maximum value of lambda, we have the delay with no extra replicas, and when lambda goes to 0, we can create essentially an infinite number of replicas, and the lower bound converges to 1. But the policy we just described doesn't coincide always with the lower bound. We have that it's a linear interpolation of the lower bound for certain points. But actually, when r star times k is an integer, the lower bound and the asymptotic delay of a policy coincide. And in the middle, there's a gap, but we conjecture that this gap is because our lower bound is not tight and not because our policy is not asymptotically optimal. Now, in the case when k goes to infinity, it's slightly different. Now, when lambda goes to 0, r star goes to infinity, and the lower bound thus goes to 1 as well. But when lambda tends to its maximum possible value, R star tends to 1 and the lower bound goes to infinity. But the nice thing is that actually an asymptotic, the asymptotic delay of our policy always coincides with the lower bound. So in that case, we truly have an asymptotically delay optimal policy. Okay, so in terms of the practical issues, how many replicas are too many? Well, R star per task are too many, and this is surprisingly independent of Kn and of N. Regardless of what's Kn and N, R star per task destabilize the system. Should we adapt replication level to congestion? No, only the routing, because we send replicas to idle jobs, well servers, I'm sorry. And also, should we make more replicas if it's taking too long? No, we saw that always making the same amount of replicas at the beginning is already optimal. And most importantly, should we create bigger jobs replicate more than smaller ones? No, not more or less. All jobs should be replicated the same amount, regardless of size. Okay, so that was for one model. Now we're gonna shift to a new model that we developed, what we call a size-based slowdowns model. And this is kind of with a different motivation in mind. And the thing is, when we saw the processing times in Google's data centers, they observed that basic tasks see small variability and small tasks see high variability. And the idea behind this is that small tasks, big tasks are so large that they see kind of the average of this fluctuation of the processing rate. So they have a small variability in the total processing rate. And again, the way we were modeling is the service time for replica is the size times 1 plus slowdown. So in order to reflect this, we just assume first that kind of condition on the size, the slowdowns are ID. This talks about the homogeneity of our servers. But the key assumption is that condition on the task size, the variance of the slowdown is decreasing and convex in the size of the task. So this kind of goes with this averaging out of the slowdowns. And this is going to be key in our results. So unfortunately, our objective is still find a policy by that minimizes the expected delay, but the general slowdowns with these correlations plus the possibility of start replicas at different times make this problem intractable. Our solutions kind of make an assumption that it's a little restrictive, and is that we assume that all replicas associated with the same job start their service at the same time. We need this just to keep it tractable. And as a consequence of this assumption, we have that the service time is actually determined by a family of probability distributions, such that PR of X is the probability that our replicas start their service given that the size of the task is equal to X. So for each X, we have a probability distribution. And with this, we can create a straightforward lower bound. And is that the expected delay is lower bounded by the expected service time, given that the expected number of busy servers is at most n. So this is a lower bound for any policy that satisfies this assumption. And we cannot really solve this problem explicitly. What we can do is prove some structural properties of solutions. So first, in general, we know that if P star minimizes the expected delay, then under this P star, we know that for all X large enough, only Kn replicas are made, which is the minimum number of replicas that you can make. And also that the maximum number of replicas made is still order Kn, so it's just some constant times Kn. And in the special case that Kn is equal to 1, we can have a deeper understanding of what we should do. For a case Kn equal to 1, actually we know that P star of X is concentrated onto 2 consecutive integers. And more importantly, we know that the expected number of replicas created for each task size X is non-increasing with X. So we really prove that in the case k equal to 1, bigger jobs should be replicated less than smaller jobs. And also with these solutions, we can actually create asymptotically optimal policies. So if we consider Pn a solution of our optimization problem, but instead with up to n busy server, we do n minus n to the alpha with some alpha less than 1. So Pn would leave the system in heavy traffic. And when a job comes with task of size X, we make replicas are according to distribution Pn of X. And then if possible, we're going to send it to idle servers with something like join the LQ. And with those kind of policies, and at least for the case that Kn is a constant, we know that these policies are asymptotically delay optimal. So they're actually, the delay converges to the lower bound. And with this, we can now answer our practical issues. Now, how many replicas are too many? Well, still it's going to be order km per job, but the actual number depends on the distribution of the slowdowns. Should we adapt replication level to congestion? Still no. Regardless of congestion, we only look now at the task size to decide the replication level, but not the congestion. We just do the routing according to the congestion. And should we create more replicas if it's taking too long? Well, maybe. We made that kind of restricting assumption that they all start at the same time. So our optimality claim is only within those policies. So maybe making replicas more replicas later on is better. And most importantly, is that bigger jobs should be replicated less than smaller ones. Which for the other assumption for the slowness, we should replicate all the same, but now bigger jobs should be replicated less. So to conclude, first of all, if you want an asymptotically delay optimal policy, force heavy traffic is the way to go. We need to use all our resources, create as many replicas as possible while being stable. So that's why we need to use heavy traffic. Other thing is, not surprisingly, we don't need to adapt the replication level to the congestion. Only the routing need to be adjusted to the congestion. This is expected. Other kind of surprising thing is that the job site distribution is mostly irrelevant as long as it has finite variance, so the problem doesn't become, you don't have infinite delay all the time. Then it really doesn't matter what's the job size distribution, which is the task size distribution as well. But the most important thing for me is that having the correct assumptions on the slowdowns is absolutely key. We've seen in the past in the literature that we have kind of conflicting recommendation as what to do with smaller jobs, with bigger jobs. Well, actually, you need to make sure they have the correct assumption. You need to make sure that, that the model that you're using is the one that corresponds to your application, to what you're interested in. So you can design optimal policies that are really optimal. And that's it. Thank you.